This is University Lecture. Welcome to another in a series of lectures given on the campus of Iowa State University in Ames. Today, Victor Weisskopf, professor of physics and head of the department at Massachusetts Institute of Technology, speaks on the topic, Why Pure Science? Professor Weisskopf.
I believe that pure science is useful and important from many points of view and deserves the moral support and the financial support of society. We, the community of scientists, must be prepared to answer the question whether science is important or not in a positive way, and to give arguments that convince a large part of the public to support science. This is not an easy task. It would be much easier for me, at least, if I could present you here in some nice way some of the latest results of science. And maybe that would even be the best way of making propaganda for science. But we must really try to formulate clearly what science does for society and why it cannot be neglected. Today, more than ever, pure science is under heavy attack for being useless, irrelevant, expensive, and even dangerous. And today, more than ever, scientists must be ready to counter these attacks and to set the record straight. First, let me make it clear what I understand by pure science. Pure science and basic science are one and the same thing. It is research carried out for the sake of interest in the observed phenomena and their causes and effects in the basic natural laws that underlie all phenomena. It is different from what one calls applied research, which is performed in order to be able to make better use of a natural phenomenon for some more or less well-defined purpose. This purpose is usually a practical one, based on the needs of technology, from needs that coming from outside the realms of science. It is, however, difficult to make a clear distinction, because very often a phenomenon is interesting just because it is useful. And very often applied research is necessary to perform a basic research, to get the tools for basic research. But nevertheless, it is quite clear that certain realms of science are very definitely basic, where there is no question. For example, astronomy, elementary particle physics are certainly basic sciences. In other cases, the distinction is not so clear, like if you go to solid state physics, geophysics, chemistry, biology, or physiology. There are great parts that are very near to practical applications, and therefore basic science and applied science are mixed. However, I do think that one can make a definite distinction, even if it is not always clearly applied. If the purpose of research is to recognize, to understand, to investigate the deeper connections, then we can call it basic. Now, basic science is in fact only a very small part of what one would call the science activities. In other words, a small part of what scientists do in this country. Expressed in dollars, it is roughly 10%, maybe 12% of the money which is usually called science money. It's called research and development. These are mostly practical developments and applied science. Roughly speaking, a tenth of it is basic science. Now, basic science was usually, or is still, mostly done at universities, because basic research is deeply connected with teaching, the teaching of science, It's very hard to distinguish. Good research must be connected with teaching, and good teaching must be connected with research. They're closely interwoven. In the old days, let's say 30, 40 years ago, 50 years ago, basic science was supported by the universities, essentially. It was supported being part of the teaching activity of a university, with some help from private foundations and very little from the government. But the cost of research has increased steadily, and the World War II has made a great difference in many respects. Why? Well, World War II has shown, as we all know, that basic science, or at least the results of basic science, can very rapidly be applied, well, in this case, militarily applied. And the two important examples, which we all know, are the atomic bomb, the nuclear physics applied in bombs, and second, the radar, electronics applied to radar. This is why the Second World War made such a big difference. In the post-war years, science has suddenly taken a completely different aspect as far as size is concerned and support. Well, why? The tremendous development during the war has created new ways of doing science, in particular the radar development. In fact, more than the nuclear development, has shown quite new methods, where new instruments, new possibilities were available, and it was impossible to go on in the same way as science was done before the war because of all these new possibilities. At that time, the United States has made a decision. It's a little hard to know how it was made, but it was a definite decision, namely to support science as much as it can be done. That means the science was given all money they needed to make use of the potentialities of the people who wanted to do it. This decision was arrived at certainly in somewhat haphazard way, but it was based on the tremendous success of these science-grown technologies during the war. And therefore, well, the science and scientists were put on a pedestal, and money for pure science, with no strings attached actually, was available in pretty large amounts and was accepted by the scientific community. New government agencies were created and old government agencies were enlarged. The National Science Foundation was created at that time, and the Atomic Energy Commission supported a lot of fundamental science. The National Institutes of Health supported a lot of biology, and later on the NASA supported space and astronomy. This started a tremendously fast development of science and of the scientific community. And today, about the money which is invested in basic science activities reaches over $3 billion, which is quite a lot of money. Can I have the first slide, which describes this development? Here is a scale, actually only from 58 to today, and this is the main curve. Now this is a logarithmic curve. I hope that the non-scientists in the audience will not be worried about that. And this is total basic research. You see it was below 1 billion in 58, and it is now well above 3 billion. There are other curves of interest. This is the total research. This is the federal research, federal supported research. So 2/3 of the total basic research is supported by federal sources. The rest is supported by private source, industry, etc. And in comparison, you see here the gross national product, which you see here increases less than scientific activity. And here's the number of graduate students enrollment. Now you see, I didn't bother to put down what happened before 58, but that curve rises roughly that way. Well, this is a tremendous rise. In fact, you see that you get a factor 2 increase in 4 years, in a little more than 4 years. This is about 20% a year. And an increase that's really quite fantastic. And this increase also explains many of the phenomena which we have seen in the life of scientists. One should say that this includes a good deal of space science, which is called basic, and one can have a little discussion whether that's really basic or not. But it is about 0.66 of a billion here at this time is actually from NASA. So it is not a decisive amount, but a rather large amount. Now, one can be of the opinion that this development was too fast, a doubling time of 4 years. But there is no question that this development was quite very beneficial to science in the general sense. And it hasn't caused many negative effects of quickly acquired wealth that one may expect. For the United States certainly became the undisputed leader in basic science of the world. It has set up a large number of excellent first-class research institutions full of first-rate scientists, homegrown or imported. And the amount of mediocre and unnecessary work, certainly it exists, was still kept rather low. One should say, if one looks at the literature, scientific literature in this country, the amount of mediocre work is probably even less than in some other countries where the increase was less strong than here, which is probably due to the authority of a large number of first-rate scientists in leading positions and a reasonably good, well-organized systems of checks and balances which is exerted by the peers. Now, the rise, as you see, went on roughly in this tempo from the beginning to something like 64. Then you find a certain flattening out. Now, maybe particular around 68, then it flattens even more. In order to estimate what this flattening out means, one must be very careful, in particular in the last years where there was a lot of inflation. And one should correct the numbers, in particular here, with the inflation factor. And then when you do this, you see that it flattens out considerably here and then, in fact, turns back in the last 2-3 years. Now, this is really the bad thing, and this is which we have to analyze and then to discuss whether this is what it means. Now, it should also be kept in mind that such a turn down is really not only a turn down of money. I mean, less scientists can work, but it's even stronger than it is indicated here because science is getting more complicated, and therefore, even if you want to have the same number of scientists working, one needs somewhat more money every year because of the growing complexity of the instrumentation. Now, I would say that one could, of course, say that the slowing down, let's see, after 64, is something that one can perhaps, for that may be some good reasons, because the 20% annual increase is, of course, could not be maintained forever. If we maintain a 20% annual increase, pretty soon everybody in the United States will be a scientist, which may be good, but it would be difficult. Now, it is very disputable what is the right amount of increase, and we will talk about this a little later. But certainly, the decrease, which we then see from 1968 on, that is the most dangerous turn of events. What has happened in our society that reversed this trend? Was it the recognition that science has received too much money relative to other activities? Well, if it were only that, the danger for science would not be so great, because there would be certainly this kind of disturbance which I've talked about, but later on, when then the right level has been reached and the further development would go again upwards, then it would not be so great. It would be only transient effects. But I think the situation is much deeper. Today, science is really attacked, and it's attacked from two major fronts. One front comes, if I may say so, from the right and the other from the left. The attack from the right is that, from the establishment, if you want, is that pure science is just a luxury. These people maintain that the search for deeper insight into natural phenomenon is an expensive luxury, which should be supported only if it promises some return reasonably soon, some payoff in terms of practical applications for industry, for medicine, or for national defense. And the study of nature for its own sake has no public value and should not be supported by the government. And we have done too much. That is the attack from the right. Now, the other front comes from the left, or let's say from, I would say from a significant part of the younger generation. But the underlying ideas are not restricted to the young at all. This attack is based upon a distrust of science as being the source of technical innovations, most of which have led and will lead to a further deterioration of our environment, to an inhuman, computerized way of life, which would destroy the social fabric of our society, and to more dangerous applications and destructive applications in weaponry, and it would lead us to worse wars and wars of annihilation, and to further developments of our society towards Orwell's 1984. At best, it is maintained, pure science is a waste of resources which would be better devoted to some immediate socially useful purpose. Well, caught between these two wedges, science is threatened and its spirit is undermined. Now, are these attacks justified? And how can we, well, I say no. And how can we counter-attack those attacks? That is the main theme of this evening. Now, obviously, science is bearing the brunt here of a public reaction against the mounting difficulties in modern life. Now, this is not the place to analyze these difficulties, but I would like to say a few words about which I believe are the main causes of these suddenly appearing, not so suddenly, but these difficulties that appeared in the last few decades. I think that one can divide this into two parts. One is that it has to do with the technological expansion, obviously. And one is the rate of technological expansion in time, and the other is in space. And let me say a few words about this. What do I mean by this? The rate of technological expansion in time. The technological expansion changes our way of life. It changes our way of life to a certain rate. We live differently from the way we lived several years ago, several decades ago. Previously, let's say 50 years ago, or 100 years ago or more, these changes were relatively slow. It means a new generation lived more or less like their fathers and mothers lived. And therefore, they could use, they did never believe they could use, but they could in fact use the experience of their elders. Today, they also don't believe it, but I think they really cannot use the experience of their elders. Why? Because we are now coming to a period where the changes in our way of life, in our thinking, in our organization, are so fast that within 30 years, which is one generation, they really change, so to speak, qualitatively. And that is a new and unsettling phenomenon in the development of mankind. It wasn't so before. And we have to adjust to this. And maybe make the changes less strong, I don't know. But anyhow, this is a new thing for us. The second point is the effect in space. This is on the surface of the Earth. 50 years, 100 years, 200 years ago, the effects of technology on our environment were pretty bad, but they were restricted. There were always enormous amounts of the surface of the Earth which were left alone, where one could go if one had enough of civilization. But now this is no longer so. The effects of civilization have now encompassed the whole Earth. There's no place on Earth where one doesn't see, notice, and experience the effect of the environment, of the technological development on the environment. Now, I don't need to expand on this. A lot of this has been said, especially recently. But also this fact has unexpected and disturbing consequences, and we don't know yet how to deal with them. Now, these two things are effects of technology. In fact, I would even go further and say they are effects of badly applied technology. Still, since technology is to some extent, not completely, a result of scientific development, of science, of basic science, then people push it all off, push the whole responsibility on basic science and say, all right, it is science that has the fault, and therefore we have the anti-science, the strong anti-science feeling and reaction around us. Sometimes it goes even further and says science and technology use rational methods. The rational methods have brought us into that mess. Therefore, rational thinking is no good, and we have to think irrationally. Well, you laugh, but many people would probably applaud to this.
Now, it is our task to prove the futility of that argument about the moratorium in science.
I want to show that both the results of basic science and, even more important, the spirit and the attitude which basic science engenders are necessary in order to face the difficulties, to find ways to overcome them, and to create a better world in which we want to live. Now, let me first talk about the connection between basic science and today's problems. I mean the problems of which I have alluded to. I want to show that what I call the spirit and the state of mind of basic science are necessary and indispensable for the solution of the problems, of these problems of today. Now, it is even more important, and this is the second point to which I come afterwards, namely that this spirit and the attitude of basic science is also important, maybe even more important, for the creation of a more positive and constructive attitude towards the values of our life and of our civilization. Now let me substantiate this. First, why do we need basic science for the solution of our problems? And I say it again, I mean not only the results of basic science, but the state of mind which basic science creates. Well, what is the state of mind? It is an interest in understanding what is going on around us, in our surrounding. An urge to observe, to classify, to follow up a phenomena for the sake of the phenomenon itself, and to drive deeper, to probe deeper in subjects by experimenting with nature, by using one's ingenuity to study phenomena under special and unusual conditions, all in order to find connections and dependencies, causes and effects, laws and principles, one looks for order and meaning in the flux of events. It is a kind of passionate search for a better insight in things and what happens around us. This spirit of basic research is necessary for the solution of our pressing problems, because it trains people how to search for causes and effects in a systematic way, independent of any ulterior aim. See, many of the troubles facing us today are caused by unforeseen consequences of human action on the environment, for example. Now, just as I said, since the effects of all the accumulated technical developments are now spanning of the whole Earth, the totality of Earth's surface, therefore we face here a complicated network of physical, chemical, and biological causes and effects. Many of them are only partially understood, and it will need a lot of painstaking research, basic research, before these problems can be tackled. And if we try to apply technical solutions before the conditions are well investigated and understood, then one probably will worsen the situation and not improve it. But there is also another point in basic research, at least in part of the modern basic research. And that is this: the environmental problems which we are facing will require a collaboration of many kinds of experts: physicists, chemists, engineers, biologists, and geologists. And this will be scientific work in large groups, which has its own problems and difficulties. And I believe that modern basic science is a good training ground for this. In particular, some of them, like astronomy, high-energy physics, and now also biology, where a large teamwork is necessary, where you need experience from many sides, and in particular in high-energy physics, for example, where experiments are done in groups where you need almost anything. You need theorists, you need electronics, computers, vacuum techniques, engineering, cost accounting, and the psychologists. Now, if I say this, when I say this kind of thing, the following remark is often made. If you need that kind of training, why don't you let these people right away work on the problems which face us? You know, that's the same kind of attitude. Well, the defenders of this kind of this view compare the situation with the teaching of Greek and Latin in high school. They say, well, why do you teach Greek and Latin in high school? Usually it is said because then you get a good feeling for languages. Why don't you right away teach them Russian and Italian? Now, this comparison is fallacious. And that's a very important point. And in order to make this point clear, I would like to quote Michael Polanyi, by the way, who I think gave the Carlson lecture several years ago. Let me quote it in the following way. He says, "The scientific method was devised precisely for the purpose of elucidating the nature of things under more carefully controlled conditions and by more rigorous criteria than are present in situations created by practical problems. These conditions and criteria can be discovered only by taking a purely scientific interest in the matter, which again can exist only in the minds of people educated in the appreciation of scientific value. Such sensibility cannot be switched on and off at will for purposes alien to its inherent passion." See, in fact, there are two sides to this argument. One concerns the analysis of a situation, that it is just the attitude which is brought in by basic science, which you need here, which is most conducive to get an objective picture of the fact. In basic science, a search goes on for phenomena and connections in all possible directions. Whereas in applied science, the trend is directed towards a more specific goal. But there's also another side to it. That is, new technical, probably new innovative ideas will be needed. And the basic science attitude has always led to more innovative things than applied science. There are many examples for this. I just want to quote you a few. Actually, may I do it again by quoting somebody? Casimir has given a speech on this which was very impressive. He said, "I've heard statements that the role of academic research in innovation is slight. It is about the most blatant piece of nonsense it has been my fortune to stumble upon," as he said. Certainly one might speculate idly whether transistors might have been discovered by people who had not been trained in or had not contributed to wave mechanics or the theory of electrons in solids. It so happens that the inventors of transistors were versed in and contributed to the quantum theory of solids. And he goes on, one might ask whether there would be nuclear power because people wanted new power sources, or whether the urge to have new power would have led to the discovery of the nucleus. Perhaps, only it didn't happen that way. And there were the Curies and the Rutherfords and Fermi and a few others. And so he goes on. I don't think I should read the whole thing. The argument presented here is really a pedagogical one. It says that basic science produces people with a certain state of mind, which we cannot do without in this situation. Now, I believe that past experience has borne this out. See, there were many times in which large practical projects were facing us under emergency condition, projects that appeared immensely difficult and almost impossible. And the scientists from basic sciences have always played a decisive role in it. Well, so far most of these examples unfortunately come from war-related projects, such as the ones I was mentioning before, I mean, radar and the atomic bomb, which were developed by basic scientists. And I think it was essential because there completely new approaches were needed. But actually, it is not only war problems where this happened. I mean, many basic sciences have contributed lately, for example, in the development of the arms control problem, the stopping of bomb tests, and are in fact involved in all these environmental problems of today. It is true that today's problems, and that is an important point, are to a larger extent related to human relations, and to a lesser extent definable in definite terms of technological aims. But nevertheless, the problems deal with nature, with our natural environment, and therefore necessarily contain prime questions related to natural science. And just because of this fact, that the problems are to some extent not natural science problems. I mean, for example, the problems of pollution, to a great extent, problems of how do you get people not to pollute. All the technical ways are there, not always, but in many cases, technically there, but you have to prevent them from. Or the problem of birth control. These are all problems, to some extent, social and political problems, dealing with the behavior of men in complicated and rapidly evolving situations. And clearly, these are aspects to which the methods of natural science, at least today's natural science, are not applicable. And seen within the framework of that science, these phenomena exhibit some instability and a multidimensionality for which our present scientific thinking is inadequate. And it must be applied only with great care. But that doesn't mean that one will not find sometimes methods to deal with these problems, and the social sciences are working very hard to get there. There's an important qualification I would like to make. I do not want to say that basic scientists, natural scientists, are the only people we need to solve these problems. Far from it. It will need a collaboration between all kinds of people, basic and applied, engineers, physicians, social scientists, psychologists, everything else. But the argument says that people trained in basic science will play an important and irreplaceable role. They are necessary. They're not sufficient, but they're certainly necessary. But this necessity requires that vigorous basic science activities must be maintained. Today is, of course, much harder to maintain this, not only because of the money that went down, but also because of the critical situation. Not only the anti-science psychology, but even also the fact that many young people would not like to work on basic science problems when immediate things are here that worry them. Now, since this basic science period is so important, we have to do more, not less, to get young people into basic science. And I think that some of our scientists are really wrong when they say this is an emergency situation like in the World War II, and therefore we should stop basic science for the duration and all go and solve the environmental problems and the arms control problems and many other, the birth control problems, many other important problems. But the trouble is that this duration will be long, at least I would think 1 generation. And as I said before, if you cripple basic science activities today, we will not be able to build it up again. World War II interrupted our science activities only for 3 years because people went into the war work only after the war started. That is recoverable. 10 years, 15 years, 20 years is not. V-Day, Germany. But now, I would like to come to the deeper point. Not only that we need basic science as a source of brain power for the tests and problems which we will have to face, but it goes deeper. The importance of basic science is greater than that, and the solutions of practical problems. I believe that basic science is the most powerful element in the philosophy of our time. An element which in many ways is opposed to the negative and destructive trends in today's thinking. Basic science, for example, leads to a more intimate relation between man and things in nature. It creates an awareness of the laws of nature, of the connection between the phenomena. It is ecology in the widest sense. Everything depends on everything. How the universe, the atom, and life are all one of the same thing. And I think that this feeling has created the community of scientists, which I believe is a very special community. Well, as every human community, it is full of internal fights and personal ambitions and power struggle and envy and vanity and meanness. But nevertheless, it's pervaded by a certain feeling of common aim, of a common language, the common measure of value, in scientific matters at least. I mean, most scientists derive a deep satisfaction from a new advance, even if they have not done it themselves, because one understands more. It's a greatly rewarding thing. I would say one of the greatest moments, even if they are perhaps, let's see, once a year, where you see that here again, one deep new recognition has been made. And I think that this experience is an essential element in the forming of the scientific community. But there's more. There is an important and peculiar relation in science between the traditional and the revolutionary. See, science is traditional and revolutionary at the same time. For example, Newton's mechanics and the electrodynamics of Faraday and Maxwell are still valid and alive. Actually, the orbits of the satellites are all calculated by Newton's mechanics and pretty exact. And the radio waves are calculated by Maxwell and Faraday. It's pretty exact. See, the so-called revolutions, such as relativity theory and quantum theory, did not invalidate previous ideas. They only found limitations to previous ideas. But the old ideas are still valid within these limitations. On the other hand, there's of course a strong revolutionary tendency towards new and different ideas and different methods of approach. Technological advances and novel ways of thinking are constantly introduced and change the way science works and arguments. But scientific revolutions are generalizations rather than replacements of one idea by another. Old ideas are expanded and reinterpreted on a more universal basis. Old methods and old observations are not proven wrong. They are proven impractical, perhaps, and inaccurate only. Now, the involvement in such activities, in such developments, creates a conviction that there is progress in science, that we really succeed in getting deeper insights in many aspects of the world. See, after all, one cannot but be impressed by the development of science in the 20th century, with all the new things, quantum theory, relativity, nuclear physics, astrophysics, and recently biology, which really a framework has been created for a unified description of the whole natural world and its evolution from the hydrogen gas to human beings. And it tells us the basis of why are things the way they are, why has matter the properties which we see. And this development is not finished, we're in the midst of it. But its all-encompassing character and its success in disclosing the essential features of our world, that creates a feeling of participation in a unique collective enterprise, in participation in constructing an intellectual edifice together. And I believe that this is one of the few great creations of contemporary culture. And this creates this value. There's little doubt among scientists as to the general value scales. One has certain different opinions about one science against the other, but the general value scale is there. Now, this unity of effort has also another very important value. It transcends national and political differences and has made the scientific community really international, or I should better say a-national, better than any other groups. Personal contacts across national borders are easily established, and one can talk to, science has its own language. The percentage of foreigners working in scientific laboratories is probably greater than in any other human activity. And there has been success in international collaboration more than in any other field. I would like to mention CERN, the International Laboratory in Geneva, which stands out as a true model for the United States of Europe, which politically have not yet been realized. The international ties of science have been also useful in non-scientific matters. I remind you of the Pugwash conferences, where scientists have started the bomb test stop and the disarmament negotiations and many other things. Now, I believe this collective enterprise, this common aim, is also a certain reason why the scientific community is, I believe at least, in a healthier state than other parts of society. I have read the other day statistics about drugs among students at Harvard University, according to the departments, and it turns out that the science school has much fewer drug addicts than the rest. Maybe that has something to do with it. Now, how can one transfer these supposedly healthy symptoms to a larger part of the population? Let me show the next slide just to bring in a jocular vein. The next slide is from the New Yorker magazine. I hope this is known in Iowa. And here you see a cartoon of, well, it says, how many men are there with our terrible passion for knowledge? So that's the problem, you know. I hope you can read it. Lights, please. How can we transfer this? Now, the most important vehicle, I believe, is the role of basic science in education. The young people should be exposed to a larger extent than it is done now to science. And this can be done on almost any level. Scientific education can be done at elementary school level, at high school level. In fact, elementary school level plays an important role because intelligent play with simple natural phenomena can transmit this joy of discovery and a deeper appreciation of our natural environment. Now, in higher education, it's obvious that active participation in scientific research is a very important thing, that students should absorb the spirit of science And we do not do enough of it. And I come to this later. They should have this, the facing of unsolved problem and the participation in finding something, a new insight. It should be very fascinating to youth. It should hold the interest of the young people because, after all, it should give them an aim and purpose in life with all the wonderful new problems which we have to solve, like structure of matter and the universe and the thinking problem of the theory of thinking. And even some trivial example, we don't know today what really makes a liquid a liquid. If there were no liquid, if a theoretical physicist would never have predicted a liquid on the basis of our present atomic knowledge. So there are lots of problems have to be solved. Now, I never understand why actually modern youth isn't, I don't understand why they are set against basic science. Actually, the spirit in basic science, to my mind, is very similar to some of the current feelings in youth. This trend to be more intimate with nature, to have a deeper contact with the understanding and with natural phenomena. True enough, it is hard work, but it's very rewarding. I believe, for example, that one could easily call basic science is a sort of a glorified flower power. When the recognition, the insight in what's going on enhances and humanizes our appreciation of nature. And that, I think, is why the attitude and this basic, the attitude in basic science is very close to the attitudes that lead to protection of our natural environment, the fight against abuses in industry, technological application, and in war, which can also be seen from the large number of basic scientists who participate in this movement. And this is also why I believe that the basic science will be useful and necessary to get a better quality of life and a better relation to our environment. Now, after having said this, however, I think I have to spend some time, a few minutes, to talk about the way in the shape in which basic science is. Because I believe that basic science can be useful in all this direction, but it will have to change some of its present ways of life. There is a doubt whether the present form of basic science really can fulfill these aims. Many of these things are due to the fast increase of scientific activities, as I have shown in the first slide. And this fast increase definitely has left its mark on the scientific community. The next slide, again from the New Yorker, will show what I mean. Here you see Eureka. So, the lights, please. You see, the greatest danger, to my mind, is the over-specialization in science. It is understandable. There are many trends that lead towards the over-specialization. The increasing pace of research. It doesn't give the researcher time enough to think about other things than his very special fields. He tries to stay ahead of his many, many competitors, and so he cannot devote much time to enjoy science. Another trend is also the availability of jobs. You know, when you can always get a job in exactly the field you're trained, why should you then be interested from a material point of view in other fields? Actually, this has produced, to my mind, grotesque consequences. The other day, all of you probably, who physicists, must have received a questionnaire from a roster of the manpower roster from the AIP, from the American Institute of Physics, where you're supposed to tell how old you are and so on, and where you're born and so on. And then, what is your specialty? And then on the other side, there's a list of specialties of which you have to choose the one you are in. And this list is fantastic. It says, for example, high-energy physicists, hadrons. high-energy physicists, leptons. And then solid-state magnetic properties, solid-state optical properties, solid-state electric properties. Now that's, when I saw this, I just crossed it out and wrote physics. Now, the students, you see, they expect, when they make their thesis in solid-state magnetic properties, to get a job in solid-state magnetic properties. And this, of course, fantastic. How boring a life, you know, how narrow a view. All your life you should do the same thing. And I mean, a physicist should be interested in all sides of physics. I mean, he's interested in nature, in the phenomena. A physicist should understand nature. That means he should know. The wonderful thing in physics is this, in a way it's all the same. It's the same quantum theory. It is the same electrons, the same protons, the same laws that govern all physics. That means a physicist, by definition, must understand at least the essential things in depth, all part of it. And that goes, of course, exactly for biology and for any chemistry, for any other science. And here is, of course, where we have made the mistake. I mean, we, that means the teaching generation. The teaching of science must change. It must return to the emphasis on the unity and universality of science. It must move away from the fabrication of expert craftsmen, as you have seen here in a specialized trade. It must bring fields together. And the task is difficult. Because, you know, there's what I said before, there's competition, there's a heavy demand on time. But on the other hand, it's highly rewarding. If one is deeply imbued by the importance and significance of one's ideas, one ought to try to transmit them to one's fellow men in the best possible terms, or at least to one's wife. Now, look, I'll give you an example about sort of the wrong value scale that is here. Take music. In music, you see, the interpretive artist, the pianist, has very high esteem. In fact, an effective rendering of a Beethoven sonata is considered as a much higher intellectual feat than the composition of some minor piece. Now, can't we learn something here? I think that a really good presentation of some result, some scientific result, some scientific insight, even if it is well known, but difficult, is a much higher and intellectually much more challenging task than some little original new discovery. Now, after all, let's not forget that the scientist helps himself by seriously attempting to explain his work to the layman or even to the scientists of a different field. Usually he cannot explain his work to an outsider, and you have seen it and heard it and experienced it many, many times. But I believe if he cannot explain it to his fellow colleague in another field or to the layman, then I believe he hasn't understood it himself. And a much more concerted, systematic effort towards presentation and popularization would be helpful in many, many respects. It would be a potent antidote to overspecialization. It would bring out clearly what is significant in modern current research, because not everything is. And it would also make science a more integral part of the culture of today. Now, let me at the end only make a few remarks. More remarks. And I'm coming back to the mundane question of how much money. Because how shall we really say, what is the right support of basic science, what is too much and what is too little? Now, I repeat again that the question is not only how much, but also how it is changed. And before I should talk about how much money, I think the main thing is that science planning should be done on longer range. That's unfortunately very difficult in the United States government structure. But science can only reasonably develop, and many other things too, if there are long-range planning so that one knows how things are going to be in 5 years and not suddenly going up or down. In this respect, some of the European countries have a much wiser science planning because they have usually 5 years projections that are kept. The European lines do not go up that fast, but they are steady, and that is, as I said, more important. Look, Europe always copies America, and usually the bad things. And I think this downturn may be copied in a few years, but so far it wasn't. Now, what would be roughly a measure of what is the right support? Now, I believe that the key to this question is the educational purpose of science. Science and education must be mutually involved. And in order, the higher educated schools, the major schools of higher education, must maintain a vigorous, and stimulating, and lively research activity. Now, therefore, I would, very roughly speaking, I would say that the science support of basic science should be such that the teachers, the professors in major research institutions can devote, let us say, half of their time to productive, stimulating, and modern research. Then I think there will be this interplay between students and teachers that is so necessary to establish that spirit and that attitude of which I have talked about. But we must be careful that this is done, that this support is not skewed, is not divided in one science gets more than the other. It should be done in the spirit of basic science. It means the choice should be not determined by the returns, the practical returns, but by the interest and by the frontier value of the different fields. Now, some science are expensive and some are not. Radio astronomy is more expensive than, let's just say, certain branches of biology. But that doesn't mean that they should be less supported. We should have in all those fields that are at the frontier and that are modern and that are vigorous and stimulating, we should have that kind of support that is necessary to keep, as I said, a vigorous scientific research, 50% of their time, for the teachers. So this ties the science expenses to the number of students. And clearly it won't be 20% a year. And therefore, it won't be so that clearly every PhD in science will be absorbed in the field in which he made his thesis. In fact, probably not. Probably only a smaller percentage, maybe 10 or 20% of the finished PhD will be reabsorbed in the actual research process. But that is good, because what we really need is that the spirit of science spreads. I think that science PhDs, especially when they are trained in this more general way, should go into politics, into business, into industry, not only as specialized scientists, but as human beings who do other jobs, administration and other jobs, just like in other fields. If you study English or you study law, you have a much wider range of jobs than exactly what you have made your thesis. And I think it is one of the dangers of the present society that the science attitude is not integrated in the life of the nation. Now, it may be fitting to close, again by a quotation, and I would like to read to you an exchange of words between Senator Pastori, and Robert T. Wilson, who is the director of the new Proton Accelerator Laboratory, this new giant accelerator in Batavia, Illinois. Now, Senator Pastori asked Wilson, is there anything connected in the hopes of this accelerator that in any way involves the security of the country, the defense of the country? Dr. Wilson, no, sir, I do not believe so. Senator Pastori, nothing at all? Dr. Wilson, nothing at all. Senator Pastori, it has no value in that respect? Dr. Wilson, it only has to do with the respect with which we regard one another, the dignity of men, our love of culture. It has to do with those things. It has to do with, are we good painters, good sculptors, great poets? I mean all the things that we really venerate and honor in our country and are patriotic about. It has nothing to do directly with defending our country, except to help make it worth defending.
You have been listening to another in a series of lectures given on the campus of Iowa State University in Ames. Today, Victor Weisskopf, professor of physics and head of the department at MIT, spoke on the topic, Why Pure Science? University Lecture is a presentation of Iowa State University Radio.